I'm Katie. I'm a student at Purdue with Professor Andres Arrieta, and I'm presenting flexible mechanical sensors with time-dependent viscoelastic responses. So the motivation for this project is that as structures like wearables and soft robots need to become more adaptive and responsive, they need large arrays of sensors in order to detect objects and forces and interact with unstructured environments. And there's also research in aerospace about putting large arrays of sensors over airplane wings that can detect changing aerodynamic loads. So with these applications come different challenges, which include you have to have sensing over these very large areas, withstand high strains, and you also run the risk of data overload. So having these big arrays of sensors can generate a huge amount of data, which can be difficult to process in real time without issues like buffering and lag. So we want to create a compliant sensing metamaterial that has filtering and signal amplification directly incorporated, and we want to achieve spatiotemporal sensing. Our inspiration comes from nature. So natural structures use mechanics to efficiently filter and amplify external signals. One example is honeybee legs. They have resonant frequencies at frequencies that they use for communication dances across the hive. And there's joints in bird wings that show thresholding. So under certain aerodynamic conditions, they will change the shape of the wing. So having these capabilities of filtering and signal amplification directly incorporated locally at the sensor reduces the burden on your central processing unit, which is the brain for an animal, what would be like a computer for an engineered system. So we already had worked on this compliant metamaterial that's composed of this sheet of bistable domes. And as you can see, it's very compliant and it's highly reconfigurable. So we think it has potential as a sensing skin. And we asked how we can use the special mechanics that you get with the bistability to make a mechanical sensor that reduces the need for post-processing. So we're trying to sense external forces and use bistability to make it more efficient.
Would you mind making that go away? Pushing the cross. Yeah.
Okay.
Oh, there was something down there.
Okay. So first we're going to zoom in to the unit cell here. So the unit cell is composed of a bistable dome. So I have a big one here. Basically, it's stable in this ground state. So right now it's not strained. But if I push it hard enough, I can overcome a force threshold, this energy barrier that corresponds to some minimum force, and it inverts and it's stable in this inverted state as well. And at the base, we put a piezo-resistive strip. So piezo-resistive means if the strain changes, the resistance changes. And you can see the base around this dome is curved. So that strip will be curved and the resistance should change. Okay. We're 3D printing these using fused deposition modeling, FDM 3D printing. So the white material or green in this picture is thermoplastic polyurethane or TPU. And the strip is printed with PLA, polylactic acid, that contains graphene, which makes it conductive. So here I have a unit cell, so the dome with the piezoresistive strip, and I'm cycling it by inverting the dome up and down, and this plot is showing the resistance readout of our sensing strip. So you can see the first few cycles are a little bit different. That's because you have some initial strain softening, and some of the electrical connections in the conductive strip are permanently broken. But once you reach steady state, you can see that there's these two distinct resistance levels that indicate if you're in the inverted state or the ground state. So you could probe your resistance here, and you would know that you're in the inverted state. So a force large enough to invert that dome must have occurred at that unit cell without having to actually look at it. So that threshold force gives us one of the special capabilities, which is the reason that we're using this bistable structure as a sensor, and that's having built-in filtering. So normally that would be done by post-processing, but here we incorporate it directly through mechanics. So I'll show you how it works. schematically first. So if I just apply a small force, that's not enough to invert the dome, right? So if I just push on this a little, it doesn't invert and it stays in the same stable state. So if you read out the resistance of your strip at the bottom, your final resistance is exactly the same because it's still in the unstrained ground state. But once I exceed the threshold force, you trigger snap through, which you can see in the force plot here, and your final resistance is much higher. So the fact that this force occurred at that unit cell is recorded in the material properties of your sensor. So this force is filtered out, and this force is recorded just through the mechanics of the bistability. And where that threshold is can be tuned through your material properties and your geometry. So here's a comparison of two different domes that have the same parameters, except the left one is thinner and the right is thicker. So for the left one, if we apply an 18 Newton load, you can see that triggers snap through. And if you look at the resistance readout, your final resistance is higher. So the fact that that load occurred is recorded. Whereas for a thicker dome is harder to invert. So if you apply the same 18 Newton load, it doesn't invert the dome, and you can see your final blue line resistance is at the same level. And you actually have to go up to 22 Newtons, so that's the light green line shows inversion, and your final resistance is higher. So you can tune where that threshold is using your geometry and material properties. We can also change the signal amplification, so how much this resistance changes between the ground and inverted states. And we can do that by changing the design of our unit cell. So if you look at the FEA, most of the stress and strain are going to be right by your inverted dome, like you'd expect. So we can move our sensing strip farther or closer to the dome to change that signal amplification. And our experiments confirm this. So this is an 8 millimeter radius dome, and we place the sensing strip at 3 different distances. For the farthest one, you can see the light green line. It's only about 5% change between the ground and inverted states. But once we put it much closer at 10 millimeters, we get 50% change between the states. And since we're 3D printing these, we don't have to be limited to a linear sensor design. So we can actually print a curved sensor that follows these stress and strain contours. And if you look at the FEA, you can see the curved sensor has much more uniform compressive strain along the length of the sensor. And so with the same experiment with a curved sensor, we can get up to 100% change in resistance level between the ground and inverted states. So we have filtering and signal amplification that are achieved just through the mechanics of the bistability of the sensor. So now we take these unit cells and we pattern them into an array to create this metamaterial sheet that has spatial sensing. So we can read these resistances and know that a force must have occurred at these 2 domes, and it must have been above the threshold that we programmed by the design of the unit cell. So next, we wanted to also be able to remember the loading history of the sheet. And for that, we use viscoelasticity. So, you know, a viscoelastic material has this dynamic mechanical response, and it'll change over time. So this is a stress relaxation test on TPU, and you can see you have relaxation over time, and this is fit to a Prony series, so you have this exponential decay. So with viscoelastic materials, there's actually a narrow range of geometries where you can create what's called a pseudo-bistable structure. So bistable, it holds the inverted state, and pseudo-bistable, it temporarily holds the inverted state, and then it snaps back by itself. So with this, you still have a force threshold to invert the dome. So you still have the filtering and the signal amplification capabilities, but now it self-resets. So this is more useful for cycling. Okay, and then we're also going to change our piezo-resistive material from one that's PLA based, so PLA is a more elastic material, to one that's TPU based, which is a more viscoelastic material. So this is cycling a pseudo-bistable dome up and down with the 2 different sensor materials. So on the top is the more elastic material, and you can see the ground state resistance is very consistent, and the inverted state resistance increases and then levels off. So sometimes this is exactly what you want, 2 distinct levels that tell you what state you're in. but we're interested in the viscoelasticity. So here, doing the same experiment, you can see the inverted state resistance has this exponential decay, and the ground state resistance changes linearly. And what's really interesting is that I'm showing 13 inversion cycles here, and it actually has distinct resistance levels in both states for all 13 cycles. So you could probe your resistance here, know that you're in the inverted state, and that dome, that sensor has been inverted 11 times. So this ability to count and remember that sum is inherent to the metamaterial through the mechanics. And we see similar trends with different geometries with pseudo-bistable domes. So this is a thicker one. The magnitude of the strain energy is larger, but it's the same trend. And this is interesting if you compare it to conventional memory systems. So like electronics, transistor-based memory is all using binary. So you have 0 and 1. So if you wanted to store bigger and bigger numbers, you need more and more bits to keep having a unique series. So the number 13 is actually 1101. So it takes 4 bits to store. And here we're showing a single unit that can represent 13. So looking to the future, that's interesting because there's more and more interest in having mechanical systems that can show sensing and memory, but it's very, very difficult to compete with, transistor-based memory for size and efficiency. So if we can move beyond conventional binary, that might be one way to increase the memory density and make these mechanical systems more competitive. So to summarize, we showed this metamaterial that has bistable units that give us filtering and amplification. And then we use viscoelasticity to make them pseudo-bistable with the same capabilities. And we also use viscoelasticity to have counting and memory directly incorporated. So in the future, we'd like to explore this memory more and also look at scaling these down. So thank you very much. I'm happy to answer any questions, and I have samples if anyone wants to see.